Hi. Well, I decided to start a research project. So the first thing that I'm gonna do is we're gonna create our models for the two type of the choices that you have. um, the first thing that I'm gonna do is I'm gonna do the Yagi Uda. So for this case, I'm gonna start by looking at the specifications of the antenna. So it's an array of Yagi Udas. So consider the 7 elements and fire Yagi Uda antenna shown below for 600 megahertz. So the frequency operation is 600 megahertz. Okay, so the Yagi antenna is a famous based on concept of mutual coupling between dipoles. The distance between the driven dipole and the reflector is 0.1 lambda wavelengths, and between the driven dipoles and the directors is 0.15 lambda, and between the different directors. Okay, so first of all, I'll start by creating my geometry, and based on the description of the problem, this is what I have. I have the reflector, I have the driven dipole, and the directors. So the distance between the driven dipole and the reflector is 0.1 lambda. The distance between the driven dipole and the directors is equal to 0.15 lambda. Make sure also to note here is that they don't give us any information regarding the length of the dipole. So we assume the dipoles to be halfway lambda. So when we enter geometry, we'll just go from 0.25 to minus 0.5. That makes like the distance, if you add up that together, makes it equal to 0.5 lambda. Okay, so another thing to mention here is that that they say that big pattern axis okay, so the maximum, okay, so another key point here is just to this is just in terms of like getting the right geometry. The antenna has a maximum in the forward direction, y direction, meaning the pattern, the beam pattern of the antenna, it's pointing into the positive y direction. So if you notice here, my dipoles are aligned in the x directions, and then it's pointing in the positive y directions. Okay, so we'll start creating my geometry in EasyNet. So the first thing that I'm gonna do is I'm gonna start from opening the file that's called dipole 1. So this file already has they're like basic files that they're already created. So then you can just follow. I mean, you can just basically start from those files when you create your own geometry. Okay, the first thing that I'm gonna do is I'm gonna start enter the frequency of operation. The frequency of operation is equal to 600 megahertz. Okay, since most of the dimensions are given in wavelengths, so I'm gonna change that from meters to wavelengths and wavelengths. Okay. The other stuff that I need to do here will be plot type, okay. So now we are ready to enter our geometry. Let's look at the antenna. View antenna. So as you notice, the dipole is not facing, are not along to the XY. I mean, not along the X axis. So I'm just gonna rotate that and to the wires. I'm gonna create change rotate wires. So I'm gonna rotate the wires 90 degrees. So it's gonna be either counterclockwise or clockwise. Our rotation axis is gonna be C, and the angle is gonna be 90 degrees. Okay, so now we have that. Okay, now we start with the dimensions. So let's look again back into our geometry, and we say the dimensions are 0.25 to minus 0.25. Okay, so that's gonna be in terms of lambda. Okay, so this is equal to minus 0.25, and this is gonna be 0.25. The diameter of the wire at this point is not very important, so we just assume it's gonna be like that, and that's, we have our first wire. Okay, so we have our director right now, driven element. So the other thing that we need to do right now is also enter the reflector, the driven, and the other elements, the directors. So from here to here, the distance is 0.1. So what I'll do here is it's just gonna be, I'm gonna make these, I'm gonna shift it over to the minus y direction by minus 0.1, then minus 0.1. Okay, so that's gonna be our reflector. So we have a reflector right now, and then we're gonna create now our driven element, 0.25, and this is gonna be at 0, 0, 0.25, and this is gonna be 0, 0, and the rest is the same, so you just type enter. Okay, so where we have there or reflector and director, driven element. So now we need to create our driven elements. Okay. Right. So the distance between the driven elements are, so this distance right here is 0.115 lambda. Okay. So we create another one, 0 minus 0.25, 0. So no, this is gonna be, let's look again, 0.15. So it's 0.15, 0, 0.25, 0.15, and this is gonna be 0. Just enter. So more or less it's coming like this. So the next one, so we got, this is a 7 elements Yagi Uda, so we have to put another one, we still need to do 1, 2, like 4 more. So it's 0.25. This case is gonna be, this case is gonna be 0.30, 0.25, 0.30, 0, enter. The other one is gonna be minus 0.25, 0.45, 0, 0.25, 0.45, enter. So that's 1, 2, 3, 4, 5. Okay, so it's 5, 6, 7. We need another 2, so it's 0 0.25, 0 0.60, 0, 0 0.25, and 0 0.60. Enter. And this is the last one, minus 0 0.25, 75, 75, 0, 0 0.25, 0 0.75, 75. Okay, so we got our Yagi Uda right now. Okay, let's look at them. Okay, so that's what we got. The geometry, we have already the geometry entered. Okay, let's keep reading the problem. And the problem says that assume that the driven dipole has a current of 1.0. Calculate the phases on each dipole element so that antenna has a maximum forward direction in the positive y direction. You can assume that the reflector and the director have currents magnitudes of 0.9, and then each of the directors have a current of 0.5. So in this case, we're gonna simulate the antenna by we're gonna put sources into it. So the way we're gonna simulate is like we're gonna enter each one of them will have a current, and also will have a phase associated with that element. So in this case, they give us what's the current for each one of them. So for the first wire, which is the reflector, we are assuming that wire 1 has a amplitude of 0.9, and the phase will derive the phase based on the equations that I'm gonna do in a different lecture. But right now I'll just enter the phases here so you can be able to start working on your project. But there will be another recording where I will solve the equation related to the phases. So for phases here is gonna be assume this is already calculated. So the phase for the first element is gonna be 0.2 times 180. So it's gonna be 36 degrees. And the type of source is a current, so that's what the problem gives us. For the second one, the source is gonna be in wire number 2. It's gonna be 50% from 50% meaning at the middle of the wire, and the amplitude of the current is gonna be equal to 1, and the phase of the driven element, it's gonna be equal to 0. For the third wire, it's gonna be the same, 50 in the middle of the wire, and the phase is equal to minus 54 degrees. The amplitude is equal to 0.9. So we have a 0.9, and the amplitude and the phase is gonna be minus 54, and it's a current. For the fourth element, for wire in the middle, the current is equal to 0.6, and the phase is equal to minus 108. Enter. The fifth wire is gonna be have a current of 0.6, and the phase is equal to minus 162. For the sixth wire, 650, same current, 0.6, and the phase in this case is gonna be minus 216. And the last wire number 7, screen in the middle, 0.6 current, and the phase is equal to 270, minus 270. Okay, all right. So so that's about it in terms of the geometry. Okay, we'll close these, and we'll generate the pattern, and this is the pattern that we got. Okay, so we could either change the elevation plane plot type to be a three-dimensional. Okay, and then this is the plot for the three-dimensional pattern. So you know it has like the pattern is on the maximum in the y positive direction. So we can actually look at the azimuth plane and the elevation plane and show it 2D dB. Okay, so we can see that the maximum dB is 7.41, and this is in the elevation plane. In this case, it's gonna be the E field, or okay. When we calculate, we're gonna calculate those, but E field and H field, that's what the problem asks you. The azimuthal plane, this is what we have. It's 7.41 degree maximums, and you can get all the parameters: beam width, front to side lobe, outer ring, and many other things. Okay, so this is it for the Yagi Uda. For those who are like working in this problem, then this is what they need to do. Okay, stop.